Hi everyone, I'm Shannon, and today I'll be talking about DPrio, efficient differential privacy with high utility for Prio. So for some background, I'll first explain what Prio is, and we'll look at an example use case where Firefox would like to collect browser telemetry, so information such as content blocking statistics from its users. So here, Mozilla would like to learn some aggregate statistics about things like content blocking from its users without violating their individual privacy. So we're looking at things like sums and means here. And Prio enables us to do this privately and securely. So Prio is work from 2017 by Henry Corrigan-Gibbs and Dan Bonet. And the idea here is that they introduce a second non-colluding server. So imagine we have one server controlled by Mozilla and one controlled by Let's Encrypt. The users will secret share their data to these two servers and also send along what's called a secret shared non-interactive proof. So this snip will sort of verify that this data is well-formed. These servers can then collectively verify these snips and then compute whatever aggregate statistic they want. So essentially, the secret sharing ensures that the individual non-colluding servers don't see the original data, while these snips prove that the data is well-formed. So this is usually something like a range proof. And this doesn't prevent clients from submitting arbitrary values that are still within this definition of being well-formed. And the reason why I have this asterisk here on this privacy property is because the servers ultimately learn nothing about the client's private data except for what they can learn from these aggregate statistics. But the problem is that aggregate statistics are known to be vulnerable to what's called reconstruction attacks. So given some function like a sum or a mean, you may be able to reconstruct the original client's data. And we can solve this by using something like differential privacy. So if you add a little bit of noise to the output, then you can prevent this sort of reconstruction. And so a natural question to ask is whether or not we can integrate differential privacy into Prio. Now, we'd like to do this efficiently. We don't want to impose too much computational overhead on either the clients or the servers. And we'd also like to do this with high utility so that the statistics that we're computing are still useful. And so there are two sort of baseline solutions for doing this that we'll compare against. The first is an MPC-based approach where servers compute a distributed noise generation protocol. So they'll collectively perform this protocol to sample some noise value and add this to the final result. This is high utility. It's sort of in this central model of DP where you're not adding too much noise to the output. But it does impose this additional computational overhead for the servers. On the other hand, you could have a local DP-based solution. So in the local DP-based solution, clients will individually add noise to their data before sending this to the servers. So they'll send secret shared noisy values to the servers, who will then accumulate the result, which will include that noise. And this is efficient. It's really easy for these clients to sample a single noise value and add it to their data. But we have to add noise on the order of the number of clients, which could damage the utility. Now, this might be acceptable for some cases. So for example, this is the approach that Apple and Google take in their exposure notification privacy preserving analytics paper. But we want to know if we can do better. Can we develop a solution which is more efficient than the MPC-based approach and has higher utility than the local DP-based approach? So this is what we do in our work. We call our solution DPrio, and it works as follows. So we have our clients here, each with their data points. Each client will sample a noise value from some distribution. And then as before, they will secret share their data among these servers. And they'll also secret share these noise values among these servers. Now, these data points will be verified with these secret shared non-interactive proofs, just as they were in Prio. And the clients will also include snips for the noise values that they submit. So now these servers can verify that everything is well-formed by verifying these snips. And then what they'll do is they'll run a noise selection protocol. So a multi-party computation protocol which allows them to choose one of the noise values that they have received from all of the clients. And then they'll take the sum of this noise value with whichever statistic they've computed and output that result. And this gives us differentially private output. So let's look at the noise selection protocol in a little bit of more detail. Basically, how this works is that each server publishes a commitment to some random value, row 1 or row 2. This is something like a hash. And then they'll reveal their random values, row 1 and row 2, so that they can each verify each other's commitments. And then all they do is they select the noise value at index row 1 plus row 2 modulo the number of clients, and then they can verify the SNP of this noise value. So this commit reveal protocol ensures that no server can sway the result towards any particular client. And this noise selection protocol can be generalized. They can rerun this protocol C times for some small constant C to select multiple different noise values. And clients can sample smaller noise values that might sum to some other distribution. So a couple of requirements for this to work. We require that noise values follow the same encoding structure as the data points, and this is so that we can use the same corresponding SNPs to verify the validity of the noise values as we do with the data points. So we don't ensure that noise values are sampled correctly, only that they are well-formed. But this doesn't really pose an additional risk because we have the same assumption on the data points. We can't prevent arbitrary data being submitted as long as it's well-formed. We also assume that malicious clients make up only a small proportion of the total number of clients, and this is reasonable in settings where Prio is in use. Usually there's clients on the order of millions, and this gives us the property that the probability of selecting a malicious noise value is low. And so in terms of DP guarantees, if we assume M is the number of malicious clients, and C noise values are selected, and C is greater than M, then we get sort of a typical epsilon delta DP guarantee, as you might expect. But if C is equal to 1 and is less than or equal to the number of assumed malicious clients, then the client whose noise value is selected may be able to distinguish between the true database D and some neighboring database. And so this gives us a failing probability of M over N, where N is the total number of clients. So in general, we consider protocols that add C greater than 1 noise values. But in the case where C is less than or equal to M, M the number of malicious clients, we end up with this extra failing probability here at the end, which essentially captures the probability that you only end up selecting noise values from malicious clients. And this additional failing probability delta decreases exponentially as C approaches M, and when C is greater than M, it's equal to 0. So that's just visualized in this graph here. Okay, so in terms of evaluation, DPrio does have a constant time client computation. This is from the sampling of the noise value, and they have to send that additional secret shared data. But this is a fairly low overhead, and we think it's generally reasonable. In terms of server computation, DPrio has this noise selection protocol that has to be performed, but this can be done in constant time, and so it's comparable with things like plain Prio and local DP, whereas the MPC-based approach has a more complex noise sampling protocol. The MPC-based approach has the best utility still. This is in like the central model of DP because they only really have to add 1 noise value, whereas DPrio has to add a constant number of noise values, but this is still much better than the local DP case where you have to add noise on the order of the number of clients. And finally, we don't make any additional assumptions on the required number of honest servers, whereas the MPC-based approach does assume at least 2/3 of servers are honest. And so we've provided an alternative protocol which integrates differential privacy into Prio, which has less computation costs for the servers than the MPC-based approach and better utility than the local DP-based approach. And I'm happy to take questions.
Okay, I'm still looking for questions in the chat. Oh, here's one from Ryan Wales. Could the noise be generated by the servers instead of the clients if you make a similar assumption about the majority honesty of the servers? Or are there just too few servers in realistic settings to guarantee you get some honest noise?
Yep, you can definitely have servers generate noise values as well. We go into more detail in the paper about generalizing this approach, but there's various ways of combining noise generations from clients and noise generations from servers and getting different trade-offs from all those different approaches.
Well, the question that I wanted to ask was, I thought that DPrio was compatible with statistics that couldn't be computed just from sums from the client inputs. Maybe I'm wrong about that, but if so, it seems like it would be difficult to add the kind of noise or what you would need in order to get differential privacy with those statistics. Is that true, using your system?
Yeah, so it's primarily for aggregate statistics. We haven't extended to things like heavy hitters or medians or anything like that. I think it would be interesting future work, but right now it doesn't quite fit in with the way that we add noise. Yeah.
Well, we still have time, so if somebody wants to ask a question and would raise their hand, we could do it that way. Yeah, I see one in the corner. I'm going to just bring this over.
Thank you. This is more of a conceptual question. Usually, the privacy notion that the DP provides is not compared to the privacy notion that multi-party computation and other techniques as such provide. So these are two different privacy notions. Why do you think it's appropriate to look at them and compare them in this context, as you were in your conclusion slide?
Sure. I mean, in terms of the privacy guarantees that come from the multi-party computation protocol, that essentially just guarantees that servers don't learn anything about the data, whereas the differential privacy guarantee puts some bound on the amount of information that you learn from the output. So they sort of address two different parts of the protocol, one of them being during the whole computation and the other being on the output.
Thank you. You still have time for more questions if there are additional questions. Or maybe I should check the Zulu. Okay, if there's nothing else, let's thank the speaker again.